maybe you've seen a simple harmonic oscillator. Probably you've seen a simple harmonic oscillator. Lots of things are almost like a simple harmonic oscillator. So what I'm going to do in this video is to show you 3 different solutions that are of different forms to the simple harmonic oscillator. So let's just imagine the simplest case of a mass on a spring in the x direction, and it has some velocity, has some initial position, and it's attached to a spring. There's no friction, there's no anything else because it's magic. So we have the force due to the spring depends on the position, because the further you stretch it from the equilibrium position, the greater the force. So we have something like this for the force, and that's going to be equal to the mass times acceleration. And here's the physics trick. I mean, it's just because we're kind of cool. But we write, instead of writing the second derivative of position as the acceleration with respect to time, we're going to write that as mx double dot. So that x double dot is the second derivative. It's second derivative with respect to time. It makes us look cool, and we like that. We like to look cool. So we have this equation: negative kx equals mx double dot. That's the equation that we want to solve. Okay, I'm going to show you, we want to model real stuff. I'm going to show you something that's not real, but we can pretend it's real, and we're going to use this for other things too. And that's a mass oscillating on a spring in Python. So I made this, and I'm not going to really go over the code, but I think that we can agree that it's a good simulation of reality. So let me run this. So there's my mass oscillating on a spring. I know the mass. I know the spring constant, k. I know the initial position. I know the initial velocity, and then it goes on forever. Or it goes on for 5 seconds, which is ever in this case. So if you want to know how to make this, I have a video I've already done on this, but I can show you again later if you want. Basically, it's just calculate the force, use that to update the velocity or momentum, and then use that to update the position. And this is the Euler method. So, I mean, it's a numerical calculation. It's not an exact solution. But we can treat it like it's real. That's the important point. Okay. So when I solve this differential equation and get an analytical solution, I want to go back and check and see if it agrees with this. That's why it's there. Okay. So let's go back to the paper and let's do our first solution here. So here we have this differential equation. I'm going to write it a little bit different. Let's write it as x double dot is negative k over mx. That's my differential equation. And this says, this pen is kind of like not making me, it's kind of not vibing with me. Let me try a different pen. This says that I have some function of x. I take the derivative twice with respect to time, and I get the same thing back with this negative constant in front. So one way we can do to solve this is to just guess. I'm going to write here guess, because it's important. I'm just guessing, right? I'm using my vast knowledge of derivatives for things that you take the derivative twice and you get a negative sign. And one of those answers is trig functions. So let's just say this. I'm going to say x as a function of t is a cosine, depending on t, and I can't just take the cosine of time, right? Because time is in seconds and cosine is a ratio. So we have to have something like this: cosine omega t, I don't know what omega is, plus b sine omega t. So that's just a guess. Now, if I guess something and then I test it and it works, then I win. Okay, so let's take the derivative of this twice and see what we get. So I'm going to take the derivative of it once, x dot as a function of t. So the derivative of cosine is negative sine, so I get negative a. But then I have to take the derivative of the stuff inside. The derivative of omega t with respect to t is omega. So I get negative a omega sine omega t. And then the derivative of sine is cosine, so I get plus b. I got to take the derivative of the inside, omega cosine omega t. Now let's do it again. X double dot is going to be equal to, now I'm going to take the derivative of this. I get cosine, so I get negative a. I get another omega. I got to take the derivative of the stuff inside again. So I get negative omega squared cosine omega t. And then here I get negative sine, so I get negative b omega squared. Again, I got to take the derivative of that stuff. Omega squared sine omega t. So right here, let's factor out the negative omega. I get negative omega squared. Omega squared times a cosine omega t plus b sine omega t. And so that is x. So this is a solution if it doesn't matter what a and b are for the solution right now, but I do know that negative omega squared has to be negative k over m in order for this to work. So that means that omega equals the square root of k over m. Okay, so that's the solution. Now, suppose I want to find these constants a and b. So suppose I start at t equals 0 at some position x0 with some velocity v0. Let's use that to find the value of a and b. And I ran out of room here, so let's just, I'm a poor planner. Okay, so let's say x of 0 equals x0, x dot of 0 equals v0. There's some values, and we can check this with some actual numbers. So I had this as my x. X as a function of t is a cosine omega t plus b sine omega t. I'm not going to put parentheses there because I think we all know that's fine. And then x dot of t was negative a omega sine omega t plus b omega cosine omega t. So let's go ahead and use this value right here. I know that when t is equal to 0, this has to be equal to x0. So I can say x0 equals, I'm going to put in t equals 0. Let's write it out. A cosine of 0, right? Because I have t is 0 times omega. It doesn't really matter what omega is. Plus b sine of 0. Well, right here you can see that sine of 0 is 0. So this is 0. So that means that in cosine of 0 is 1. So I get x0 equals a. Okay, now let me point out something here. This is the initial position is equal to a. This is not the amplitude of my oscillation. Okay, because in this case, since I start with a velocity v0, then it's going to keep moving before it reaches its final point. So I'm just letting you know that don't say, oh, a is the amplitude. A is the amplitude only in the special case where you start it from a velocity of 0. Okay, so now let's look at the other situation over here, x dot of 0. X dot 0 is going to be negative a omega sine of 0 plus b omega cosine of 0. I'll put parentheses around that. If I don't put parentheses around the 0, it looks like sino and coso, just so you know. And that's going to be equal to v0. So here, now that term is 0. So in that term's 1, so I get b omega equals v0, and b equals v0 over omega. Okay, so now I have my whole function. Let's just write it out. I have x as a function of t equals a, which is x0 cosine, I put the parentheses there again, I'm not sure why, plus b, which is v0 over omega sine omega t. And let's just check the units here. This is, omega is the angular velocity in radians per second, and so that's going to make this whole unitless quantity inside, so that's good. This has a units of position, and that has no units, so I do get position from this term. Here I have meters per second, and I divide by 1 over seconds, right? Omega has units of 1 over second. So this gives me units of meters, so that's good too. Okay, so this has meters, everything works out. Okay, let's plot this. In my model that I had on Python, I have the following. M equals 0.1 kilograms. K equals 7 newtons per meter. Newton, yeah, that's right. V0 equals 3 meters per second. And X0 equals 0.1 meters. So let's use these so that I can calculate omega, right? Omega is that's a square root of k over m. So I need k and m. And then v0 and x0 and v0 I'm going to put in. So I can plot this. I can calculate and plot it. So the first thing I'm going to do is plot the position of my numerical model that we'll consider real life. And then we'll plot this and see if it agrees. And then we'll move on to the next thing. Okay, so let's switch back over to Python. Here we are. I'm going to make a graph. Let's add a graph in here. So let's just say g1 equals graph. X title equals t in seconds. Oops. And then y title is, let's be x in meters. And you don't have to put that. I'm just trying to be a proper person, right? And then I can, let's say width. Width equals, let's do 400, height equals 200. That way it'll show up really well. And then I'm going to do f1 equals g-curve, color equals color.blue, and I want to plot that. Okay, so I've already calculated all my stuff down here. All I need to do is add in my plot. So I want to plot x versus t, so I can say f1.plot t ball.pos.x, and that should work. Okay, and then run that. Okay, so that's what we'd expect. And notice right here, okay, you can see in this graph, let's cut this down to a shorter time, like 2 seconds, just because. Oh, my graph is nice and small. Okay, so you notice it starts right here. That's the initial position. It's not at 0, and it's not at the amplitude, because it was moving away. So it moves away and then back down, but it is a trig function. Okay, so now let's just calculate. Let's just call this x1 equals, let's calculate a and b. So up here, I'm going to say, I'm looking at my equation, a equals x0. Okay, I'm going to write it out because it just makes me feel better. And then b equals, I need omega. Omega equals square root of k over m type. And then b equals v0 divided by omega. So down here, x1 is just going to be a times cosine omega times t plus b times sine of omega times t. And then I'm going to plot that. F2 dot plot. Did I make an F2? Let's make another graph. F2 equals G curve. Color equals color dot red. And let's plot that. So F2 dot plot T x1. And run it. And you'll see it looks red because those two graphs are right on top of each other. You can't tell the difference. They're right on top of each other. Identical. Okay. So that did work. So that's the first solution. Okay, let's do another solution. That's actually 2 solutions in one. But let's jump back over here and go back to solve a differential equation. Okay, so I'm going to start with the following differential equation. Let's write down the differential equation again. So I have this. X double dot. That's a terrible. Look at how bad that is. X double dot is negative k over m. I'm having trouble. Okay, x. Now I'm going to guess another solution. Let's just say this. X equals a cosine omega t plus phi. So I have some extra angle here that I don't know. But you'll notice here that this is going to be a solution. I'm going to show you in a second. But I have 2 parameters. It's a second order differential equation, so I'm going to need 2 parameters. So there I have a and phi. I don't know what those are. Let's just make sure that it is a function. So x dot as a function of t, that's a solution, is going to be equal to negative a omega times sine of omega t plus phi. So when I take the derivative of cosine, I get negative sine. The derivative of this stuff is going to be omega t, the derivative of phi is 0, so it doesn't show up. The second derivative, x double dot, with respect to time, is going to be negative a omega squared cosine omega t plus phi. So there you go. So this is equal to negative omega squared times x. And so that is a solution, just like before. Okay, but we need to find how we're going to find a and phi. That it is a little tricky, right? Because I can do this. X of 0, I know that's equal to x0, and that's going to be equal to a times cosine of 0 plus phi. So even if I know that value, I don't know a and I don't know phi. So let's just write this as a cosine phi. Okay, and then I can say x dot of 0 is going to be equal to v0, and that's going to be equal to negative a omega sine, I don't know why I put parentheses there, sine of phi, right? Because here t is 0 too. So I have two equations, but I don't really know, I don't know what anything is. Okay, so let's write these two up here. So I have x0 equals a cosine of phi. And then down here, I'm actually going to divide both sides by omega. So I get v0 over omega equals negative a sine of phi. Now, there's a trick, okay? Life is full of tricks, and sometimes you have to play around to find these tricks. But what I'm going to do is square both sides of this. So I get x0 squared plus equals a squared cosine squared phi. I'm going to square both sides of this. I get v0 squared over omega squared is a squared. That becomes plus sine squared phi. Now I'm going to add these two equations together. You can do that, right? If I add the left-hand sides and add the right-hand sides, that's fine. So I get x0 squared plus v0 squared over omega squared equals a squared times, I'm going to factor it out, cosine squared phi plus sine squared phi. And what happens here? Well, in this case, you can see that cosine squared phi plus sine squared phi is 1. So that term's gone, and I get a equals the square root of x0 squared plus v0 squared over omega squared. And I know that looks painful, but it's fine. Don't worry about it, it's fine. And you may also see, oh, we're squaring terms here. And that's really what we're doing, is trying to find one way to do this is using conservation of energy to get the exact same equation. And this is the amplitude. This is the amplitude. So if you think about it in terms of energy, when it's at its maximum position, it has 0 kinetic energy, and you can use that to find the position. But now I have x0, v0, omega, I can find a. Now I can go back up here, and now that I know a, I can find phi, right? So let's write this. I don't need the squared version. So I'm going to write x0 equals a squared. And I'm just going to leave it as a. I'm sorry, a. I'm just going to leave it as a cosine of phi. And then I can say divide both sides by a, and I get cosine of phi equals x0 over a. Phi equals the inverse cosine of x0 over a. Now, there is one problem in that a is actually going to be, when I take the square root, I get plus or minus. Okay, so do I want a to be positive or negative? Let it up here kind of let's just plot it. If we get the wrong answer for a, we change it. Okay, so I'm going to change my function and plot this, but I need to first calculate a and phi. Okay, so let's do that. Switch back into Python. Let's just call it x2, right? So I'm going to go down here. I need to calculate my new a. I guess I'll just call it a2. So I'm going to say, is that big enough? Let's say a2, and this is for the second solution, is equal to the square root of x0 squared plus v0 squared divided by omega squared. And then phi is going to be equal to, what did I say? Inverse cosine, a cos of x0 divided by a, a2. Okay, so now down here, I can calculate that. Let's calculate that. x2 equals a2 times cosine omega times t plus phi. And I'm going to plot that. I'm going to plot x2. Let's see if that works. I have a feeling that it's... Actually, I know it's not going to work. Okay, so there you go. And you'll notice that it's wrong because we chose the wrong sign of A. So let's go back up here and just make that negative. And then do it again. And then boom, on top of each other. Okay, we got one more solution. And this is nice. You could do the exact same thing with sine. You get a different phi value, but it all works. I'm not going to do that. Okay. Back to paper. So here we are. I'm going to write down the solution, the differential equation, and solve it. Oh, that's the wrong pen. That's the right pen. Okay, so we have this. Ooh. My pen's dying. I might have to switch back to that other pen. I didn't like it, though. Okay, oh, here's another pen. Let's see how this one works. X double dot equals negative k over mx. Let's guess another solution. So remember, we're trying to find solutions when I take the derivative twice, I get the same thing back with a negative sign. And the answer for that would be, if you take the derivative twice, you'd get the same thing back if it's an exponential. But if you want it to be negative, then it can't be negative exponential because then that would cancel when you take the derivative twice. So the answer is to do this. X as a function of t equals, I guess I'm going to call it a again. A e to the I omega t plus b e to the negative I omega t. And that, yes, is the I is the imaginary number, the square root of -1. So let's just check and see if this does indeed work. So let's take the derivative with respect to time, x dot as a function of t. The derivative of e to the I omega t is e to the I omega t. But I need to take the derivative of the stuff up here, so I get an I omega. So let's write this as I a omega e to the I omega t. And then I need to take the derivative of this. I get minus I b omega e to the negative I omega t. Now let's take the derivative again. X double dot as a function of time is going to be equal to, now I'm going to get another I omega. So I times I is -1. So I get negative a omega squared e to the I, that's the e to the I omega t. And then here I get another negative I. So that's going to be equal to, that's going to be negative times negative is a positive. And this is going to be negative I times I is -1. So I get negative b omega squared e to the minus I omega t. And if I factor out the negative omega, this is negative omega, I'm sorry, I did it again, negative omega squared times a e to the I omega t plus b e to the I minus omega t. And that is the solution. So that's good. Now we need to find the parameters a and b, so let's do the same thing. A as a function of x at 0 is x0, and I'm going to put in 0 for t. So if I do that, I get e to the 0, which is 1, plus b e to the 0, which is 1. So I get a plus b. And then if I do the same thing down here, x dot at 0 is v0. So I put in t is equal to 0, that's 0, that's 0, so I get I'm going to write it this way, omega a minus I omega b. And so I have two equations, two unknowns. How do I solve that? Again, here's we're going to use a trick. I'm going to divide both sides by omega I for this one. So this becomes v0 over I omega equals a minus b. Now here I can multiply and divide by I. And so I times I down here is -1. So this becomes, and so I have the I up there. I have negative I v0 over omega. You don't actually have to do that, but. And then if I write this equation up here, I have a plus b equals x0. Now I can add those two equations. So a plus a is 2a. b minus b is 0, and then I get equals x0 minus I v0 over omega. And I want to solve for a, divide both sides by 2. I get a equals x0 over 2 minus I v0 over 2 omega. Now I need to find b. Well, b is just going to be b equals x0 minus a from that. So I say b equals x0 minus a, so minus x0 over 2 plus I v0 over 2 omega. So here I have x0 minus x0 over 2. That's going to be x0 over 2. So I get x0 over 2 plus I v0 over 2 omega. And that's b. Okay, now I want to plot that. And you're like, but how are you going to plot that, right? Because if this is my solution, this is actually a complex number. Yeah, it looks like it has a real and an imaginary part, and so does this. So we can't really plot complex numbers simply. We can do them complicatedly, if that's even a word. I'm looking for, I ran out of paper. Okay, let me get another piece of paper. One more piece of paper. Okay, so one of the things we're going to need to do is, I'm going to move this right here because I need those values, is to use the Euler identity. The Euler identity, and I'm not going to prove this, it says this: e to the plus or minus I theta is equal to cosine theta plus or minus I plus sine theta. So if I use that with my solution, so here I have, I'm going to write it out, x as a function of t is a e to the I omega t plus b e to the minus I omega t. I want to replace this with cosine theta plus I sine theta, and this with e cosine theta minus I sine theta. So I get a times cosine of theta, not theta, I'm going to say it's going to be equal to omega t. So it's going to be cosine omega t plus I sine omega t plus b cosine omega t minus I sine omega t. Now, if I multiply this out and group the cosines together, I have an a cosine omega t plus b cosine omega t. So it's going to be a plus b cosine omega t. And then the i's are going to, the I sine omega t, I have a, and then I have a minus b. So it's going to be plus a I minus b I sine omega t. Now, I mean, we can see here that in order for this to work, I mean, a and b, they're going to have to do something, right? But we already found a and b, and we found a and b. So let's get this parameter. Let's just call this c, and let's call that d. So c is going to be a plus b. So right here, I have a plus b. I have a and b. So this is going to be x0 over 2 minus I v0 over 2 omega plus x0 over 2 plus I v0 over 2 omega. Oh, look at that. These cancel, and these add to x0. x0. I like that. That's nice. Okay. And then d is going to be a times I minus, or let's just say I times a minus b. So now I have a x0 over 2 minus I v0 over 2 omega minus b, which is going to be x0 over 2 minus, there's a plus, right? But I'm subtracting it, so it's minus I v0 over 2 omega. So now these cancel, and I get 2 of those, so I have, and the 2's cancel because I'm adding them. So I get negative I times I v0 over omega, and that's going to be just 1. So it's just v0 over omega. So now I have my function, if I want to plot it, is going to be x is going to be equal to c, which is x0, cosine omega t plus v0 over omega sine omega t. And you know what? I already plotted that one, right? Because that was my first solution, right? So what I did was I took this as an exponential and just converted it back to trig function so that we could plot it. And there you go. Now, and you may be thinking, why the heck would you do it this way if you can't even plot it? Well, it turns out that in a lot of other solutions, this format is more advantageous, and I don't want to go over that right now, but I just want to show you that that does indeed work. So hopefully that's helpful. Simple harmonic motion, three ways. That was 3 ways. There you go. If you have any questions, just let me know down here. Okay, bye.